Hey everyone, and welcome. Today we're jumping into a really cool question from the world of AI. How can a program, which is really just a bunch of simple instructions, start acting in a way that seems genuinely intelligent? Let's dive in.
If you've ever coded anything, you've probably never thought to ask your program why it did what it did. I mean, it sounds kind of crazy,
Hey,
right? A program just does what you tell it to. But what if it could actually explain its own reasoning? That's the big mystery we're going to unravel today.
So, to get our heads around this, let's look at a classic AI setup. Picture a simple world. You've got a robot arm and a few blocks. We give it a pretty clear command. Put block B1 on top of block B2. Simple enough. The program starts moving things around, clearing a path to get the job done.
Okay, now here's where it gets really interesting. We basically hit pause and ask the program a question. We saw it move another block, we'll just call it BX, that was sitting on top of our target, B1. So we ask it point blank, hey, why did you move block BX?
And get this, the program answers with perfect logic. It says it moved BX to clear the top of B1. That's a real reason. It's not just spitting back code, it's telling us its motive. But we can push this even further.
So we press it a little more. Okay, program, I get that. But why did you need to clear the top of B1? We're digging into its chain of thought here, asking for that next layer of why.
And again, it has an answer. It gives us the next link in the chain, to grasp B1. It knew it had to clear the top before it could actually pick it up. It's explaining its own internal strategy step by step, and almost feels like it's self-aware. So how on earth is this possible?
Well, the secret, and it's actually incredibly elegant, is a powerful concept called goal trees. This is the hidden architecture that gives the program this incredible ability to reason about its own actions.
So here's how it works. When we give it that main command, put on, the program doesn't just see one big task. No, it immediately breaks that down into a series of smaller objectives, or sub-goals. First, it has to find space on the destination. Then it has to grasp the block it needs to move. Third, actually move it. And finally, let go. Each of these is its own little goal.
As the program is working through these steps, it's actually building a kind of map of all these goals and sub-goals. This map, this hierarchy, is the goal tree. Think of it like a breadcrumb trail of its own thought process. It shows not just what it did, but why it did it. And crucially, it hangs onto this map.
And this structure is the whole magic trick. When we ask why, the program just looks one level up the tree to the bigger parent goal. Why did you clear B1? Well, because I was trying to achieve the bigger goal of grasping B1. And if we asked how did you grasp B1, it would look one level down the tree to its sub-goals by clearing its top. It's so simple, but so powerful.
Now, you might be thinking, okay, that's a neat trick for moving blocks around, but is that it? Not even close. This idea is way more versatile than you'd think. Let's look at a totally different kind of system, a rule-based program designed to identify animals.
So imagine we're at the zoo and we see an animal we don't recognize. We start listing out the facts, the things we can observe. Okay, it has hair. It eats meat. It's got sharp teeth. Its eyes point forward. It has spots, and man, it is fast. Our goal is to use a set of rules to figure out what we're looking at. The system gets to work. It sees that first fact, has hair, and bam, a rule in its database fires off. Rule 1 says, if something has hair, then it's a mammal. Just like that, a new fact, is a mammal, gets created. Next, it scans the other facts. It sees sharp teeth and forward eyes. And another rule kicks in. Rule 2 says if both of those things are true, then you're looking at a carnivore. So another new fact gets deduced and added to what we know.
And here is the real kicker. Those conclusions we just made, mammal and carnivore, they now become facts that other rules can use. So the system sees it's a mammal, it's a carnivore, and it has spots. So Rule 4 fires and concludes it's a cheetah. This just brings it all together so brilliantly. As Professor Patrick Winston explained, this rule-based system is doing the exact same thing as our block moving program. It's building a goal tree. Every rule that combines a few facts to make a conclusion is just creating another branch. And because it builds this tree, it can also answer why questions. Why do you think it's a cheetah? Because it's a mammal, a carnivore, and it has spots. Same logic, different problem.
Okay, this is all incredibly powerful. But it brings up a really practical question, right?
where do all these smart rules actually come from? Someone has to program them, and that means you have to somehow pull that knowledge out of a human expert's head.
Let's use a super down-to-earth example, bagging groceries. You might go to a pro, someone who's been doing it for years, and ask for their rules. They might give you a general one, something like put the large items in the bottom. And that's a good start, but it's nowhere near enough to build a really smart system.
So this process, called knowledge engineering, has a few tricks up its sleeve. First, you get specific. Don't just ask for general rules. You ask, how do you handle milk? What about potato chips? What about motor oil? Second, you ask about things that seem alike but are treated differently, like canned peas versus frozen peas. This uncovers hidden rules and categories. And third, you just build a version of the system and see where it breaks. Every time it messes up, you've found a rule that you were missing.
Okay, for our last section, let's zoom all the way out for the final really big idea. It comes from a Nobel laureate named Herb Simon, and he gave us this amazing metaphor that completely reframes how we think about complexity itself.
Simon's core insight is basically this. A lot of the time, when we see really complex behavior, it's not coming from a complex internal program. Instead, it's often a very simple program interacting with a very complex world.
He asks us to imagine an ant walking on a sandy beach. If you were to trace its path, it would look incredibly complicated, all these twists and zags and turns. You might assume this is one genius ant with a super sophisticated internal GPS. But the reality is probably much simpler. The ant's internal programming might just be a few basic rules, like if you run into a pebble, turn left.
And that's the whole takeaway. The complex, squiggly path isn't a property of the ant, it's a property of the beach. The ant is simple, the world it's in is complex. And this is totally true for our AI programs too. The rules in the block-moving program are simple, but when they interact with a messy pile of blocks, the behavior that emerges looks incredibly intelligent.
And this leaves us with a final, really profound question to think about. It's stunning what these simple systems can do. So if gold trees and a handful of simple rules interacting with a complex world can create this incredible illusion of intelligence, what might that suggest about the nature of our own minds?
Follow for more.